Earlier this year, gravitational waves were found in what was called the discovery of the century. The Laser Interferometer Gravitational-Wave Observatory detected gravitational waves radiating from two black holes that crashed together about 1.3 billion years ago. Now evidence is building that these black holes might be primordial black holes, instead of traditional black holes. If they are, they could be the answer to what makes up the mysterious dark matter, an unidentified substance that makes up 85% of the mass of the universe, some researchers have said. Researchers from Kyoto University have published a study in the journal Physical Review Letters today, suggesting the two black holes detected by LIGO could be primordial black holes, instead of traditional black holes. This means instead of being created when stars collapse at the end of their lives like most black holes, these might have formed from the extreme density of matter present soon after the Big Bang. If further data support this observation, it could mark the first confirmed finding of a primordial black hole, guiding theories about the beginnings of the universe. The detected gravitational waves were created from a merger of two black holes 30 times the mass of the Sun, said study author Professor Takahiro Tanaka from Kyoto University. It's extremely rare for such massive black holes to form in the present-day universe. After this announcement, many astrophysicists started considering how such heavy black holes were created, and how such black hole binaries were formed. As a starting point, the team hypothesized that primordial black holes were distributed randomly in space. The universe was extremely hot and dense when it was first born. Primordial black holes came into being when gravitational collapse happened in regions which were especially dense, said Professor Tanaka. They have a completely different origin from black holes that form from celestial bodies. Using general relativity, the team evaluated how often black holes merge in the present epoch. They found that the LIGO-Virgo team's observational data on merger frequencies would fall into place if the binaries were primordial, and if they constitute 1,000th of all dark matter in the universe. Primordial black hole binaries were discussed extensively in the 1990s, however, interest in them waned when observations implied that their number was limited. To date, no one has found any primordial black holes, possibly making the LIGO-Virgo observations the first of their kind. Theoretical models about the beginnings of the universe are still hotly contested. Some models necessarily predict the existence of primordial black holes, so their discovery could help unlock important clues about the universe's early days, said Professor Tanaka. When enough observational data related to black hole binaries has accumulated, it will become possible to confirm whether these are truly primordial. LIGO's proposed successor, the Einstein telescope, will also be able to look at the two black holes as they swirl closer to each other, before the predicted head-on collision. It might be able to give a more definitive answer. The Einstein telescope is a design concept for a third-generation gravitational wave detector which will be 100 times more sensitive than current instruments. There are a few ways these black hole mergers might be distinguished from traditional black hole mergers, including the shape of their orbits. Primordial black holes would have an elliptical orbit, whereas traditional black hole orbits are circular. If these black holes exist today in large enough numbers, they could make up more dark matter, previous researchers suggested. Earlier this year Dr. Simeon Bird and his colleagues at the Johns Hopkins University, Baltimore also suggested LIGO's black holes could be primordial. They said the black holes detected by LIGO have the perfect mass to fit with a theory that suggests dark matter is made up of these primordial black holes. But so far there is no firm evidence for their existence. Interestingly enough, there remains a window for masses between 10 and 100 times the mass of the Sun where primordial black holes may constitute the dark matter, the researchers wrote in a paper. The theory behind how it happens is that if two black holes in a galactic halo pass sufficiently close, they can radiate enough energy and gravitational waves to become gravitationally bound, the researchers added. The bound black holes will then rapidly spiral inward due to emission of gravitational radiation and ultimately merge. Dark matter makes up 85% of the mass of the universe, but it is invisible because it does not reflect light. It cannot be seen directly with telescopes, but astronomers know it to be out there because of the gravitational effects it has on the matter. The team wrote in the paper that their estimates raise the possibility that LIGO has detected primordial black hole dark matter. Primordial black hole mergers are likely to be distributed spatially more like dark matter than luminous matter and have no optical nor neutrino counterparts, so would be invisible, they said. At the moment our idea is just an idea, Dr. Bird told. It's possible, but we don't know whether or not it is really true. It's an exciting possibility. For the future, we're trying to think of better ways to test our hypothesis, said Dr. Bird. More results from LIGO and related telescopes, including the European Gravitational Wave satellite LISA, will be very useful.